Hey everyone, my name's Chris and I'm an onboarding engineer here at SkyCiv. And today I'm just going to be going through an example of how to model and design a slab on ground using the SkyCiv software. So today I'm going to be using the S3D module as well as the slab design module. So I'll just jump into S3D now. And before I start the video, I just wanted to point out if there's anything that comes up in the video that you'd like some more information on, we've got this documentation library here. You can access that from the question mark. So today I'm going to be doing a slab on ground. It's going to be an industrial slab, and I'm going to be applying a pressure load to a specific area on the slab to simulate maybe a storage area or an area where there's some heavy machinery, something like that. So it's going to be a 10 by 15 meter slab. So I'll start by defining the corners of my slabs with node. And we can see I've now got the corners of my slab. So I can create a plate and I'll just go around each node there, close it up. So we've got our main slab plate modeled in now. And I want to apply pressure to a specific area on this slab. So to do that in SkyCiv, we need to create a second plate for that specific area. But to avoid doubling up on the plates, we need to create a hole in this slab first. So to do that, we can use this plate hole tool. So we can either right click and that will have that option there, or the other way of accessing the plate hole tool is to click on the plate there and this button here. But before I can create that hole, I need to define the nodes for where the hole is being applied. So we'll go back to our nodes menu there, and I'm just going to go off this corner. I might make the area 2 by 5 meters, and I might go 2 meters in from the corner. So we'll start off 2 and 2, and then we're going 2 meters wide and 5 meters long, so 7 meters for that node location, and final node there. So you can see we've now got a 2 by 5 area for our hole to be applied. Just open that up. Now, something to note with defining holes, if you hover over this tips, you'll see, but we need to make sure we put the nodes in order, and as well as the hole can't be touching the edge of the plate. So we're all right there. So we'll just go in clockwise order there. We'll go 5, 6, 7, and 8. And that's created that hole there. And I can go back into my plate tool and now draw a plate over the top of that. So I've now got my 2 plates in there, and I can apply a pressure load to this plate 2 here. And you might find, if you try to select plate 2, that it is actually selecting plate 1, and that's because they're directly on top of each other. So there's a couple of ways we can select plate 2. We can either hide the main plate there. So I was just right clicking and clicking hide, and then we can bring it back in by going right clicking again and clicking show all. The other way we can specifically select plate 2, we can go Control F or Command F to bring up the find menu. And I can just type in plate 2, and that will select plate 2 for me. So with plate 2 selected, I can now go to the pressure loads, and I'm going to apply a 10 kPa pressure load to that. And I need to specify my plate there, and I'm going to call this Q for live load. So I've applied that, and that's, you can see that that's now only applied to that area. I'm going to also create a self-weight load. So I'll turn that on and just apply that one in the -y. And I can create some load combinations. So For my strength case, I'm going to go 1.2 G times 1.5 Q, which is 1.2 times the permanent load and 1.5 times the live load. So I'll apply that, and then I'm going to create a serviceability case of G plus Q, which is 1 times the permanent, 1 times the live. And now that I've got my load combinations defined, I can assign a material and a thickness to my plates. I'm just going to turn off that load there. So we'll go to materials, and then we've got the database here. And I'm just going to use a metric concrete from the Australian code, and I'm going to choose 32 MPa, and it'll bring up all the properties there for you to check. So I'm happy with that. I'll submit that and just apply that here. So I can then go control and then drag across to select both plates, and I go into the plate menu, and I'm going to assign these plates a thickness of 200 millimeters, and I'll give them this material that we just defined, 32 MPa concrete. So we've now applied the material, and you can see in the 3D view, we've got our slab there. So we're now ready to mesh the plate, but before I mesh the plate, I just want to double check the local axis of my plates are aligned in the correct way. So to bring up the local axis for the plates, we just click the eye tool here and select this one, and that'll show the local axis. So because we're using the slab design module, we want to align this z-axis, the local z-axis, so that's that blue one, so that it's pointing upward. And the reason we do that is so that the top of this plate in its 3D view also aligns with what the slab design module will refer to as the top of the plate. Because if we leave it at the bottom, then it will be flipped. So there's a couple of ways we can flip this one over. So I can go to the plates, and I can go to plate alignment tool, and then we've got a few options here of how we can realign our local axes for the plates. I'm going to use the 2 nodes method. So I'm happy with the way that my X and Y are aligned. So I'm going to keep it aligned with the direction of 1 and 2. So I'll go node 1 and node 2, but I want to flip the normal axis. So I'll select that. And when I hit submit, you'll see that it's kept my X and Y the same, but it's now put the Z axis pointing up. So I'm now ready to mesh my plates. So there's a couple of ways I can access the mesh tool. I can either right click and hit the mesh plate button there, or I can go edit, plates, and plate mesher. And because we've got this cutout, we don't want to use the structured quadrilaterals. We want to use unstructured quadrilaterals. And then we can choose our mesh size with this slider, or specify a specific mesh size. So I know that my plates divide up nicely into a 0.5 size. So I'm going to adopt a mesh size of 0.5 meters. And I can preview that. Select all. And we can see that that meshes quite nicely. So I'm happy with that. I'll commit that mesh. So next we need to create the supports for our slab. And because this is a slab on ground, we don't want to apply the supports as pure pin. We want to apply them as springs. So I'll select all the nodes from my mesh and go to supports. And SkyCiv has this add surface spring button. If we click that, this allows us to model surface springs across all those mesh nodes. So it's already selected the plates, and we've got this modulus of subgrade reaction, and that value is just a measure of the stiffness of the soil that this slab is being constructed on. And you might get that value from a geotechnical engineer, or have some engineering judgment to choose that value. So For this case, I'm going to choose 25,000 kilonewtons per meter cubed. And I'll explain what that does in a second. And the other thing we've got is this spring type. So modeling this on soil, we want to choose the compression only spring. And the reason we do that is because if we've got a heavy load that causes the slab to heave, we don't want our supports restraining the slab back down. We want to be able to check that behavior and see whether the slab is lifting up, and realistically the soil's not going to restrain the slab back down. So we can click submit on that, and you can see that we've now got spring supports applied at each of those meshed nodes. And yeah, what that modulus of subgrade is doing, it's just taking the area of this meshed plate and dividing it into that applicable node area. So for example, I know my mesh is 0.5 meters, so we've got a 0.25 by 0.5 meter area. And if we multiply that by my modulus of subgrade reaction, 25,000 kilonewtons per meter cubed, we get a value of 3,125 kilonewtons per meter. So the other thing I need to apply is I need to apply some lateral restraints for stability of the model. Now, if you were concerned about lateral loads on this slab at all, say something causing sliding on it, you might want to model in a spring support for the lateral direction as well. Again, you could get that from a geotech or use your engineering judgment. But for this case, I'm not concerned about performance of the lateral system. So I'm just going to apply full pins in the X and Z direction there. So I'll hit apply on that. And we've now got some pins in the lateral direction for stability of our model. So we're now ready to analyze our model. And we get our results there. So we put our two load cases. We can check our reactions. You can see that's all behaving how we'd expect. We can see we're getting more of a bigger reaction towards where we've got our pressure applied. So that's all behaving normally. And we can check our plate results. So we can check deflections. So we're getting more displacement towards where the pressure is applied. We can check our moments. X, Y, and twisting moment. We can check our shears. And we can check our stresses. So lots of different results there to help you analyze your plate there. The other thing that we've got that is helpful for slab on ground, we've got this soil pressure results. So I might switch to the serviceability case because say I had an allowable bearing capacity of 100 kPa and I just wanted to check what was happening there. I can see that I'm only getting around 11 kPa. So I know that I'm not exceeding my allowable bearing capacity under my plate there. So that's a good little tool to check your bearing capacities. And the other thing that we've got is this wood armor results. And what this does is it allows you to get bending moments over a meter length in different directions. And that might help you if you wanted to complete the design and analysis of the slab yourself using maybe a spreadsheet or something that you've already got. That can be pretty useful. So the way this works is direction 1 is based on the local x-axis, which we know is running left to right from when we aligned our local axis. And direction 2 is measured directly off where direction 1 is. So with 90 degrees, that'll be perpendicular. So we're going up and down. So we need to enter in our plates. And it gives us these results here. So we can check direction 1, the top of the plate there. We can check the bottom. And we can check the other direction, top and bottom, and it gives you the results in kilonewton meters per meter. So that can be super useful for design. So with that, I'm going to move on to the design of the slab using the slab design module. So we'll just go to design here, then we've got the RC plate design. And I'm going to use AS3600 for today. All right, so we're now in the slab design module, and starting off, we need to define some structural elements. So to do that, I'm just going to click and drag across this slab here, and I can add that, and you can see that that's added to the list of elements. The other thing you can do if you wanted to get a bit more detailed, you can actually click and select different parts of this mesh here, or you can use the polygon tool and you can define specific areas that way. And we've got the inverse tool as well. But for the purpose of this tutorial, I'm happy to apply my reinforcement across the entire slab. So I'll leave that as is. So we can move across to our arrangement tab. And this is similar to how the wood armor tool was working before in the results with the 2 directions. So direction 1 is measured off the angle from the local axis of the plate, and then direction 2 is measured off the angle defined for direction 1. So I'm happy to leave this as 0, so that'll align with my x-axis, and 90 degrees, that'll be in my y direction. And then we've got the limit of the crack widths. So I'm happy to leave these as 0.3 millimeters for both top and bottom. And we can move on to our optimize tab. So this just defines the limits for the optimizer for your cover. And we can move on to the material factors. So for this, I know my concrete was 32 MPa. And I'm going to put 500 MPa for my main reinforcement there. And I'm going to leave the shear reinforcement as 250 MPa. So I'm happy with everything else there. And we can now move on to the load combinations tab at the top. So we need to define which load cases are which. So, my 1.2 G plus 1.5 is a strength case. And this is a serviceability case, and we just drop those down that way. And then we can move on to defining the reinforcement. So there's a couple of ways we can do this. We can either do it manually or we can optimize it. So starting off, I'll use the manual input. So we can click on the slab here and we click assign reinforcement manually. So we're now applying it to this full area. And the main rebar, we're assigning it to the top in the direction 1, which is along the X here. We've got our cover and our spacing, and we choose a bar size. So I might apply a mat across the top of N12s. So we'll just go select the slab there to apply it. And I'll go add. We select it again, and I might go direction 2. And that'll now give me a mat across the top. And I'm going to do the same for the bottom. And so we've now got a mat of N12 bars each direction, top and bottom. And I can add shear reinforcement as well in the same way, direction 1 or direction 2. I don't think my slab will need any shear reinforcement, but the option is there. And yeah, you just highlight that and apply it depending on what size you want. So we've got our reinforcement. We can click perform check. and we can see the utility ratios for what I've defined in the reinforcement there. We can check the different directions as well. So moment capacity there, direction 1 in the bottom, direction 1 in the top. So we can see where we would be getting a peak moment at the top of the slab, where it's that pressure is applied directly adjacent to it. We can see we're getting more of a peak there, whereas in the bottom we're getting more of a peak where that pressure is applied. So that all makes sense. We can also check our shear, and we can check our crack widths. And then it's got, if we select, we can review a table report, which will just give you all the calculations in a table format there for you to review. So I'll also show you the optimizer. I might just remove my manually assigned reinforcement, and we'll click on this here. We need to select our element there, and it will then optimize, so we'll get a nice efficient design. So we can check direction 1, and then this will actually present in the area of reinforcement required. So we can see in the peak areas there at the bottom, we need 121 millimeters squared per meter. We can check different directions. And then if we wanted to manually assign reinforcement from here, we can also add these in, and then it will recalc. So say over the top here, I might select a band there and add in some N13s. You can see now, because I only needed 50 millimeters squared before, that is exceeding what was needed there. So it's now saying I don't need anything else there based off the optimization results. So that's how to model a slab on ground using S3D, and then completing a design check using the slab design module. We hope that video helps, and we look forward to seeing some of your designs in the slab design module. Have a great day, and we look forward to seeing you soon on the SkyCiv platform.